So, today we're entering into the most important section of chemistry. Oh, it's awesome! We're doing equations, balancing equations, and we're going to just briefly open up one of my favorite subjects, and that is the mole. And it's not a small burrowing animal. It's one of the most important concepts of chemistry. It's what allows us to turn one substance into another substance. Pretty cool stuff. Okay, so let's just go ahead and kick it off. So far we have looked at molecules, right? What types of molecules have we looked at? We've looked at, in naming, we know about okay, those are subatomic particles. How about, remember when we're naming, you got to determine if it's this or this. Ionic or covalent. So those are two types of molecules that we know of so far. But what we don't know is how those molecules are made. All right, we know of them. We know what an ionic compound is. We know what a covalent compound is, and we know how to name them. Today, we're going to start to open up the great big can of worms about how we go about making them. All right, and we're going to do that with something called a chemical reaction. Can you see that on the film, John? Can you? Probably not. Chemical reactions.
Sort of, yeah.
Sort of? Okay. Chemical reactions. And that is a process in which a substance or substances is changed into more new substances. All right, so we got a process by which one substance is turned into another substance. And these chemical equations can get quite hairy. What we'll typically have is we keep track of it with chemical equations. A chemical equation uses chemical symbols to keep track of what happens during a chemical reaction. Chemical equation uses chemical symbols to keep track of what happens during a chemical reaction. And what kind of chemical symbols do you think we'll use? Oh, I didn't hang up my periodic table. Daggone it. I bought a periodic table poster so we can look at it.
You could just grab a nail and hang it.
I can do what?
Grab a nail and hang it.
Yeah, I don't think anybody at home wants to watch me hang a periodic table.
That's true.
That's true, yeah.
I don't think they will.
But that was a big giveaway. Oh, I just gave it away. What kind of chemical symbols do you think we're going to use? All the symbols on the periodic table are fair game. The way a chemical reaction works is you have reactants on one side. Then you get this cool arrow symbol. And then over here you have products. So this little arrow thing is magic. Woo, magic. That's to tell you that magic occurred. Not really magic.
Can I quit before I go to hell?
No. You don't go to hell for doing this kind of magic.
We'll be in the 8th circle.
So for instance, let's look at a chemical reaction.
You said you lost your class.
Hey,
I'm back.
come back, class.
doesn't matter, you're in chemistry class, argue about it after.
Quiet, quiet. What are you doing? Do I have to take that away?
Showing her that showing her that we will be in hell for sorcery.
For doing magic?
According
Well,
to
I
Dante.
this.
According to Dante. Dante's.
Oh, Dante's in front of me.
Dante's a mess.
All
I don't remember the
Or
So much for chemistry class.
All right, class.
Alright, sorry.
Okay, so let's take a look at this.
There's class.
Here's an example of a chemical chemical equation. What do we know?
Yeah, you could just use that.
What's this? How'd you get that?
'Cause it's
You're not
right
supposed to
there.
have that yet. Okay, what do we got? H2. What's H2? What's
I don't know.
hydrogen plus O2. Oxygen react to form what?
H2O or
Ooh, who said hydrogen dioxide? Awesome! Hydrogen dioxide. You're right. That's exactly. Not dioxide. It's dihydrogen oxide. Right. Dihydrogen oxide. Or
dihydrogen molecule.
otherwise known as
what?
water.
I was trying.
Now we've got some interesting things. We've got phase indicators. Remember phases? Phase indicators. Indicators. Is it indicators or indicators? I guess it's
No
words.
idea.
Indicators. What are some of our phase indicators? What do you think this G up here means? Elizabeth?
I think it means the phase.
Exactly. What do you think G would mean? What kind of phase would that be in? What kind of phases have we talked about?
I don't know.
Your phase diagram. Remember phase diagram? Gas! Yeah, excellent. Gas. Oh, I remember now. It's all coming back to me, just like it was yesterday, because it was yesterday. What do you think L would mean?
Actually, what does
L.
liquid?
Liquid.
Are we actually going through?
What else could we have? S. Solid.
And some other random letters that nobody ever knows.
And then we also have an extra special one, AQ.
See, I told you.
What would AQ mean?
My supposed to know.
Oh, what? Who said it?
Who said what?
You said something?
Aqua.
Okay, aqueous. Aqueous,
What
which
is that?
means, and I can't spell it, hold on, I gotta look at my aqueous, which means literally dissolved in water. Those are your four-phase indicators that you might see in a chemical equation. And we haven't talked about these guys. These are special kind of elements that don't exist by themselves as a mononucleus atom, right? Whenever you have, well, let me just write down. You have homonuclear
Write
diatomic.
these down correctly before you come to class.
Yeah, homonuclear diatomic elements. Oh my gosh, that's almost fun to say. Go ahead and say it at home. Oh, you almost got homonuclear diatomic elements. Say it again. It sound. It's like almost something lyrical. Homonuclear diatomic
What
elements.
was the word we had to learn for biology exercise? Oh, that was
Supercalifragilisticexpialidocious.
Like, it was word this long, but
Wow.
it was pretty good.
And these are elements that form individual molecules with themselves. Are elements that form individual molecules. Molecules. I spelled that wrong. Molecules with themselves. And they can't exist otherwise. You will never, well, no, never say never. You will never see most of the time oxygen just by itself or hydrogen floating around by itself. you will always see oxygen paired with another oxygen or hydrogen paired with another hydrogen. There's a bunch of these guys. We have N2, we have O2, Cl2, F2, Br2. Anyone have a periodic table? What do most of these guys have in common? What group are they in? Correct, they are nonmetals.
Are you
They
wanting
all
something
have
else?
two.
Good. That would lend credence to their non-metalness. How about a group? I'm looking for a group. Where do most of these guys live on the periodic table?
And 7A.
And what is that called?
No idea.
Most of these are halides. Halides. Group 7A. Halides. Group 7A. Now, not only did we have phase indicators, but we also have special reaction indicators. Oh, this is getting so exciting. Oh, yeah, woo, special reaction indicators. And they're not really all that special, really.
What is the last one?
Oh, too late, I erased it. This one?
Yes. No.
This one.
No.
This one.
To the left.
This one.
No.
This one.
To the right.
To the right.
No.
This one.
Left.
No.
Or left.
Left. Keep going left down.
That one. No,
Down.
right there.
Right down.
That's that.
Themselves.
Sound.
Are elements
Down.
that
That's
Yes.
themselves.
themselves.
Oh. Kind of look like thermometers. Penciler.
Special reaction indicators. And really, when it comes right down to it, they're not really all that special. But, you know,
They just have big.
don't tell them that because they get their feelings hurt. All right, and the special reaction indicators will always show up above this magic arrow.
So you don't have any on this.
I do not have any of that. Most of the time, no one really cares about what special reactions happen. They just roll with it, and you never see it anyway. But just in case you may see it, I want to give them to you. All right, so you can see this triangle, which means heat was added. Or you may see H2O, which means it was dissolved in water. Or you may have electrolysis, which means it was electrocuted. That's not how you spell electrocuted.
No, it's not.
Electrocuted. Electrocuted. It's electrocuted. I don't know, something like that. A current was added. Electrical current was added.
That triangle, is that how it's gonna look in the book?
Yep.
That messy? Or is it
It's triangle.
That messy.
It doesn't-
You just got an F for class participation. We're gonna put that down. F for grade
It doesn't
class
look quite like
participation.
a triangle.
It's a triangle. It is supposed to be a triangle.
Okay.
And an equilateral.
I was just making sure.
Equilateral?
It's a triangle, right? So that was said it was a triangle.
Equilateral triangle. All sides equal 60, 60, 60. 60, 60, 60, yeah. Hello. All right. Now, having gone over this simple but vital information, we can now progress to the wonderful world of chemical reactions. drum roll, please. That's where y'all supposed to clap and stuff. Yay! Alright. But first, why do molecules interact? You know, we look at these things. Look at all the homework that you have that you're not supposed to have yet, but you all have. Take a look at them. Why are these reacting? Why does iron and sulfuric acid form ferric sulfate and hydrogen gas?
I'm not a chemist.
Why? Well, why does any of this happen? Is it magic?
Yeah. Yep. This is that.
No, it's not magic. It's called electronegativity. What was the show where they said, the movie quote where it said that that science is often, those that don't understand science often think of it as magic or something like that. You remember what that was? Teacher's assistant, what is that? You know, it was something about, it was magic, and the guy said no, but those with weak minds often think that science is magic or something. I forget it. That's an aside. Electronegativity. Electronegativity. And really, electronegativity is the reason why everything happens. Well, God. But, oh yeah, look at that confused look. Yes, this is one of the secrets of the entire universe. Really, without electronegativity, nothing would happen.
How can you claim that?
How can I claim that?
Or like what?
Apart from what we do not know, electronegativity is the reason why everything happens.
Yeah, so as of now.
And it is the measurement of an ability of an atom in a molecule to draw electrons
How is it measured?
to itself. And negativity. It is the measurement of an atom to draw electrons to itself. Take a look at your periodic table, and we will see if we cannot come up with a rule of thumb for electronegativity. Fluorine, Fl. Most electronegative of all elements. Most electronegative of all
Are you sure it's not F?
elements.
Or FR?
It's F. Oh wait, is it F?
I think it's F. Fluorine is F.
That's a 7A. It is F.
I was right.
And then francium, Fr, is least. Given those two atoms, can you predict how electronegativity works in the periodic table?
How about
Right? So let me draw my periodic table. It looks like something like this, I think. I don't know, something like this. Here is francium. Here is fluorine. Whoops.
a guy named Frank?
Wait, where?
This is most. Yeah, most. Least.
Yeah, so it's just like as you go across, it's fine.
It increases this way, decreases this way. Electronegativity. So, if you think about it, everything has electrons, right? Some atoms have more electrons than others. I feel like singing. I'll have a blue Christmas without you. All right.
Slightly disappointed.
So, I've got this atom, and we'll call him. Here's Bob. Let's take that. I don't want that. So we have atoms. We have this atom over here who has some electrons, We got this atom over here who wants electrons. This atom over here will reach out here, steal electrons from this guy, which makes this guy unhappy, and then he goes steals electrons from somebody else. And it all just starts mismatching and cross-matching and grabbing a hold and stealing this and borrowing that. And suddenly you have brand new molecules that are formed based on this electronegativity. Alright. Not only this, but you've got, and we're going to talk about this later, you've got outer orbital, oh my gosh, what is that? Outer orbital electrons. When these electrons are all around the nucleus of an atom, as they get bigger, these electrons get further and further away from the nucleus, right? So I may have my nucleus here, and my nucleus has these electrons going around it, and the electrons that are close by are well held onto by the nucleus. But then you've got these outer orbital electrons. This is like Neptune and Jupiter, the guys that are way out there, far away from the sun. Right? And these are the guys that get picked off. When fluorine comes along here, and he's over here, and he's got all his electrons by him, he'll look over here and see this guy, and he says, oh, look at that, that's a nice looking electron. And this electron on its next orbit comes like this, and fluorine reaches out and grabs him and takes him. And this guy's lost his electron. But it's okay because some of these guys want to lose their electrons. Some of these guys have more electrons than they really want. That's why these guys are plus. They form pluses. Anything that forms a plus, like a metal is more than happy to ditch an electron. They don't really want the electrons. So they give up their electrons. These nonmetals over here take the electrons, and that is the impetus. That is what kicks the whole thing going for chemical reactions to occur. If it weren't for electronegativity, you would have atoms, you would have molecules, and they would just stay the same atoms and molecules forever and ever and ever. And you would never be able to digest your food. You would never be able to do all the other stuff that we do. All right? Now, having said that, having gotten some appreciation for reactions and why they occur, there are five basic reactions. Right? There are basically 5 reactions. What's going on here? Is there a chicken? Yeah. There are, I'll go ahead and say 6. There are 6 reactions, and you'll see why I'm hemming and hawing about 5 versus 6 in a second. Let's take a look at the 5 reactions. Or 6. 5/6 reactions. And these reactions, you're going to be responsible for being able to identify. So at the end of the day, you should be able to look at these and say, hey, this is a double replacement reaction. Or this is a single replacement reaction. Or this is a decomposition reaction. Speaking of decomposition reaction, let's take a look at it. Decomposition reaction. What do you think happens in a decomposition reaction? Yes, you in the front row. You're in the second row. You're in the back row, chemist. All right, you. What do you think? Decomp. What does it sound like?
Like, decomposes, breaks down.
Exactly, breaks down. So we have AB, magic sign, going to A plus B. And now these AB, these are just dummy letters. These aren't really elements. Although they may be, I don't know, is A and B an element? B is boron. A is nothing? Really? That's kind of sad that A is not an element.
A is not an element.
All right. So these are just dummies. So you got something going to A and B. Something composed of 2 different things breaking down to form A and B. An example of that would be H2CO3. Otherwise known as carbonic acid, magic sign, forming H2O plus CO2. What is this? What is this reaction? Everybody knows this reaction.
Separation.
It's decomposition. Decomposition, but this one right here, what is this?
Burning?
Nope. No, we're going to do that though. Combustion is one of the ones we will be doing today. This is soda pop.
What?
This is soda pop. Yes, it's soda pop.
Yes.
That's what happens when you open up your can of soda. What happens? You and all of a sudden you get H2O and CO2 from those little bubbles are CO2. Carbonic acid is breaking down. As soon as you pop the can, carbonic acid starts breaking down to H2O and CO2. What happens when a Coke gets flat? You lose all your CO2. All the CO2 is gone. You've made a bunch of water. You've watered it down. It doesn't taste as good. And you formed CO2. All the CO2 is escaped. All right? So that is decomposition. What do you think, given decomposition, what do you think another one would be?
Composition.
Composition, except we call it formation. Or synthesis. Either one. Ooh, synthesis really sounds cool.
Yes, if you can't spell it, just don't try.
Formation. I can spell synthesis. Synthesis.
Congrats.
And what do you think this is? Go give me an example of just using the A and B. What would it be?
A, B, C.
A, excellent. A plus B, magic sign, AB. It's just the opposite. And what would be an example of this? We just had it, right? That was our O2 plus H2 forming what there? Or dihydrogen oxide. What time have we got?
12:37.
Thursday.
Dad, you want me to pause the camera occasionally?
Yeah, go ahead and pause it and let's restart it so we don't end up with a video file that's